NOR implementations. And just as a refresher, the NOR state table is 1, 0, 0, 0. Now, like the NAND gate, the NOR gate is a universal gate. The inverter is just having the two inputs tied together. OR gate is a NOR gate with an inverter after it. And the AND gate is the NOR gate with the two inputs inverted. And to show that this is true, you do A prime, B prime, and then the 1, 1, 0, 0, 1, 0, 1, 0, and then the NOR of this would be which is the same as the AND gate. So another way to look at this is the NOR gate is an AND gate with inverted inputs. No, NOR. So when you can have your expression as a product of sums, you can use NOR gates to implement them fairly easily. So let's take an example from the book here. A plus B times C plus D. So A, B, C, D. Go to a NOR gate. This is A plus B, C plus D. Now, you've inverted, using NOR gates, you're inverting the outputs. So to go to an AND gate, you would need to invert the inputs to cancel out the inversion of the outputs of the OR gates. But this, as I showed just a few minutes ago, is the equivalent of an NOR gate. So let's go. Let's look at a K-map reduction. Let's say A, B, C, D. One, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, let's just use that as an example, just some random placement. And 0, 0, 0, 1, 1, 1, 0. This is A. B. C. And D. Okay. We're wanting to do the NOR implementation. So we're going to do this as a product of sums. To do the product of sums, you take you group the zeros and then invert the expression. Review from K-maps here. So you got this group, you got this group. So you got 5 expressions, or 5 terms. Let's see here, you have A and not D. A and B, or no, A and not C. Wait a minute. A, B, not D, and A, B, not C. Okay. You got A, not B, C. Not A, B, C. And then, let's see here. 1, 2, 3, 4. Which one am I missing? A, not A, not B, D. All right. Everybody see how I got that? And that's the grouping of the zeros. So it's the F prime. To make it a product of sums, you run everything through the De Morgan's law. So you got A plus A prime, B plus B prime plus D plus times A prime B plus B prime plus C, A prime plus B plus C prime, A plus B prime C prime plus C prime plus times A plus B plus D prime. Okay? Yeah. Oh, because you're doing the grouping the zeros, this form is the complement of the actual function. Okay? And then when you convert it from the complement to the actual function, you run it through De Morgan's theorem. De Morgan's law. Oh, okay. I did the A, B, and not D here. You're right. I screwed up on that one. It's not C. Not C. So this one would be plus C. This one is A, B, not C. Not C. For this group here. This would be A, C, not B. A, not B, C. And then not A, not B, D. And then A, not A, B, C. In the first group, yeah, no, you're right. You're right. I'm okay. It's A, not C, and not D. Yeah, that's yeah. Okay. Yeah, you're right. B is not included in the first grouping. So Maybe I shouldn't have done a 4x4. Maybe I should have done a 2x4. This is going to get big and messy. All right. So you have the 4 inputs. One going to an inverter, which is a NOR gate with inputs tied together. Okay. So you're going to have not A, C plus C plus D. There's a not A, plus C plus D. And then not A plus B plus not C. And oh no, it's not A, not B, and C. So C, not A, not B, and C. And not A, B, and not C. And it was not A again. And then A, not B, not C. A, not B, not C. And then A, B, D, not D. A, B, not D. All go into one big NOR gate. Does that make sense? Yeah. Mm-hmm. with if you look at the if you look at the state table, you can see that if you tie the inputs together, it acts as an inverter. You see that? So you can use a NOR gate as an inverter. So if you just all you have is NOR gates, no inverters, you can use a NOR gate as an inverter. Yes, this is D prime, this is C prime, B prime, A prime at those points. Share. Yeah. It gets a little confusing in this area here, but if you just take it one step at a time, you know, you can keep track of what you're doing. Yeah. This is the equivalent. This is the equivalent of a AND gate with inverted inputs. So because your input, because the inputs into here are inverted from the OR gates, because these are these are ORs, not NORs. So we're doing the OR, but we're inverting the output. You got to invert it again to go into the AND gate, but that's the equivalent of an OR gate. So it simplifies the design in that regard, rather than running 5 inverters into a 5-input AND gate. All right. But like I said, if you take it step by step, you know, look at each section, each term in turn, you can create these more complex circuits, logical representations. But let's see here. Let's see here. Let's do it. Maybe a little bit easier one. If don't. Okay. All right. I'll let you finish. Writing that expression out or drawing out. somebody have the homework handy? I was going to see if I could do something similar on the. Yeah. Yeah. Oh, okay. Nor implementation of the following expression from a sum of products. See if we can do that. All caught up? Okay. Need a bigger eraser. Okay. Say you're given a expression f equals a prime b plus c, and you want to do a NOR implementation of that. That is a sum of products form, and to do a NOR implementation, you need a product of sums form. So I think the easiest way to do this would be to do a K-map. A, B, C, and let's see here, 0, 0, 0, 1, 1, 0, or 1, 1. One, one, 1, 0, 0, 1, and let's see here, that's C, B, A. Not A and B. And or C. So you have 0, 0, 0 here. Okay. Now you do the get the product of sums version from this. So you get f prime would be not C and here not C and not B, B prime C prime and A C prime. Okay. And yeah. Yes. Yeah. And then do the De Morgan's magic. And And then remember, when you group the zeros, it's the complement, F prime, and then the F for the product of sums. And then from there, you can just go with oh no, I don't need A. I just need A prime. And then A prime C. And B here. See how that works? So this section is here, and this section is here. Yeah. Oh, you with the C, that means all the C group are ones. A prime, B, all the B, all those are. So these are the two groups in the product of sum of products expression. Oh, to get the K-map from an expression like this, you take each expression and okay, what is going to make A prime B 1? All the A primes and all the intersection of the A primes and the B's, which are these two ones right here. What's going to make that 1? All of the squares that fall into the C category, into the C. So all 4 of those. And then you take the complement, group the zeros, and go from there, and then De Morgan's law, change it into this. Now, if you want to algebraically go straight from this to this, you're welcome to do that as well. Might require a little bit more work, but well, on this expression, it shouldn't be too bad. That's here, A prime B plus C is, well, yeah, just the distributive property, the plus over the, so it'd be A prime plus C times B plus C, because of the distributive property, which is what we got here, just with the terms reversed. So you can, for that problem on the homework and what you may encounter on a quiz or test, you can go directly from an expression like this in the sum of products form directly into the product of sums form by algebraic manipulation. Yeah. Yeah. I'm sorry, say that again?
We invited the output coming from B or C. We use the NOR group. Also, NOR the general output from A prime or C, B or C.
Mm-hmm. Yeah, you're inverting the outputs from both of those OR gates.
So is that
Yeah, the NOR implementation uses a NOR here to bring them together, because this is the equivalent to an AND gate with inverted inputs. Yeah, remember I showed you the state table earlier? So because this is inverted, that would need to be inverted as well to make it even out. They kind of cancel each other out. And I believe the same kind of goes with the with what I was saying with the NAND gates. This type of implementation uses fewer transistors. The NOR gate has a minimum of 2 transistors, whereas an OR gate has a minimum of 3. So you're using only 4 here instead of 6, and a NOR gate has minimum of 2, and an AND gate has a minimum of 3 transistors. So you're using, 50%, 1/3 less transistors here too. So overall, this would use 6 transistors instead of 9. So it'd take up less space on a circuit board or die. It'd be cheaper to implement. Which, when you get out into the capitalist world, these sort of things matter. Yeah. I'm assuming, I was just counting the logic part. The inversion, inverters use a minimum of 1 transistor. The NOR and the NAND implementation uses 2. Yeah, it'd still be less transistors doing it this way than using inverters, OR gates, and AND gates. Well, that just about wraps things up for the day. About out of time. Have a good day.